Welcome to lesson 6.4, titled The First Fundamental Theorem of Calculus. And to this point, we've learned a couple big theorems, the intermediate value theorem, the mean value theorem, and moving into this one, noticing that word fundamental should emphasize the importance of what you're going to see here in this lesson. And the reason why this is so fundamental is because it's going to give us a way to link the initial conversations we've had about integral calculus with some of the ideas and skills that we got from differential calculus. And so let's zoom in on this first example. The velocity of an object in meters per second is given by v of t equals t squared minus 6t plus 2. And that function would be a parabola. And if we want an idea of what it looks like, we're going to come in here to our y equals menu, go ahead and graph it, and see that it appears to have a vertex at about 3. We're going to call that about -6 or 7. Its graph looks something like this. And as we talked about in our previous lessons, if we have a graph that shows velocity, this object's position could be evaluated by looking at the area bounded by this velocity curve between 1 and 4. That area would represent the change in position over this interval of time. And how we calculate it would be the definite integral from 1 to 4 of t squared minus 6t plus 2. The only skill we have to this point to evaluate it would be to use Riemann sums and approximate that area, or go back to our calculator and hit Math 9. Go with the integral from 1 to 4 of x squared minus 6x plus 2 with respect to x, and the area from the calculator graph that we copied onto our notes appears to be below the x-axis, so we should expect a negative number, and we get a -18. But I want you to think of this in a slightly different way. We could find the change in an object's position if we knew its position function. Let's call that x of t. If we knew x of t, the change in distance would just be the position at the final value 4 minus position at the start value. So again, final position minus initial position. And so what we'll look at to start this lesson off is, can we get x of t from v of t? And recognizing the relationship that v of t is the derivative of x of t, the question really becomes, can we get a function given its derivative? And the answer to that is yes. We're going to work on finding what's known as the antiderivative. Given a derivative, f prime of x, the original function f of x is known as the antiderivative. All that's to say, if we start from a derivative function, we're going to work on going backwards to find out the original function. And so on the first example, f prime of x equals 2x cubed minus 5x plus 7. And what we want to get to is the original f of x. The one that, if we were to differentiate with respect to x, would get us right back to this function here. And so what I want you to think about is, if we look at this first term, 2x cubed, can we think of a function whose derivative would be 2x cubed? Well, if we have an x cubed, thinking about our power rule, we should realize that this came from doing something to the 4th power. But the derivative of x to the 4th power is 4x cubed. And notice that that is twice as big. So if it's 2 times as big, how can I compensate for that? Well, I could make the original function half the size. And notice how this first one didn't work, but if we take the derivative of 1/2 x to the 4th, the 4 times the 1/2 would be 2, and we go down to x to the 3rd. Minus 5x, this came from an x to the 2nd power. But again, derivative of x squared would have to be 2x, not 5x. So can you think about a number that you could multiply by 2 and end up with 5? Well, in this case, that would have to be a negative 5 halves. And the 7, that's the easy term on the end. That would just go back to being 7x. The derivative of 7x is just 7. And so my original function is 1/2 x to the fourth minus 5 halves x squared plus 7x. And we know that because taking the derivative would yield 2x cubed minus 5x plus 7. Now there's one little thing that we're missing in our f of x function, and that's the possibility that we had a fourth term that disappeared when we took the derivative. Any constant on the end of our function, if we took the derivative, would disappear. And so when we think about these antiderivatives, we're always going to end them with a plus c because the derivative of any constant is 0. On this second example, we start with an x to the fourth power, which means we're going to have an x to the fifth power, but notice how this coefficient is going to need to end up being a 1. We need 5 times something to give us 1. That would have to be a 1/5. Minus this 3x cubed, going to have to be an x to the fourth power. We need something to multiply this 4 with to end up with a 3. And our coefficient here will be 3/4. And hopefully as we move this along, you start to notice a pattern in how we're building up these antiderivative terms. This 5x squared, this one will end up with an x to the third, and we need 3 times something that would give us 5. We'll have a 5/3 there, minus, we have this 1x to the first power. It's going to have to become an x squared. We'll need something to multiply with the 2 to become a 1. That coefficient is going to have to be a 1/2. The plus 5, that had to have come from differentiating a 5x. And again, this plus c. And just to formally write this note down, we could have any constant here because its derivative is 0. And so let's look at one more before we wrap up this part and get closer to that fundamental theorem of calculus. Here we have f prime of x equals square root of x minus 4. Well, just the same way we worked with derivatives initially, I'm going to change this into being an x to the 1/2 minus 4, which will give me that f of x is, this is going to have to get 1 larger. Remember, in differentiation we subtract 1, so this 1/2 had to have come from a 3/2 power. And notice I'm going to have to end up with a coefficient of 1 when I differentiate. So what times 3/2 would end up with 1? That would have to be its reciprocal, 2/3. The minus 4 will become a minus 4x, and then plus any random constant that we could think of, because when we differentiate, that will just be a plus 0. And so what we're looking at is our first basic rule for integration. And it's really our power rule for integration. When we start with our derivative being a power of x, and we want to move to our original function, what we do is exactly the opposite of how we differentiated. We multiplied by that power and then subtracted 1. We're going to go exactly reverse for this. We're going to add 1 to our power and then divide by the new exponent. Or if you want to write it in a slightly different way, we'll end up with 1 over n plus 1 times x to the n plus 1. And this is the first skill we're learning for what's known as an indefinite integral. Everything to this point was definite integrals, finding values for areas under a curve. An indefinite integral has the same operational sign, still has this integral sign out in front, but it gives antiderivatives. So the integral without any boundaries on it, no a to b, of any function of x with respect to x will be, and a common notation we use if we don't start off with prime already, notice how this just says little f of x. we generally denote the antiderivative big F of x. If we start with f prime of x, we'll just go back to being regular f of x. And every time we do an indefinite integral, and we go back for this antiderivative function, we're going to have to remember this plus c, because there could have been any constant at the end on the original function. And so with this one rule in mind, and getting this new idea of the indefinite integral, we'll start very basic. And again, notice the parallels between this and differentiation. Differentiation, we start with power rule because that gave us the ability to work with any polynomial. We're doing the same thing here. So the indefinite integral of 9 minus x squared with respect to x. For any constant terms like this 9, we've already seen a couple times, those had to have come from that constant times our variable x. Derivative of 9x goes back to being 9. Minus, and now let's try that power rule, that very basic rule for integration, which stated we are going to add 1 to our exponent, so this x squared becomes an x cubed, and divide by n plus 1. Divide by that exponent plus 1. The original coefficient was a 1, so we're going to end up with a 1 over 3. Again, notice how that if we were to take the derivative, this 3 would multiply with the 1/3 and turn back into this 1. And with our indefinite integration, the only thing we have to tack on to the end of that is our plus c. Example 2, this integral of 6 over x squared, that's going to be a little bit tough to work with what we currently know, so we're going to change that and look at it as 6 times x to the negative 2 minus x to the negative 3 dx. The same types of rewrites that we did when we worked with derivatives. And now we'll get x to the negative 2 plus 1 is negative 1, and we'll divide our first term by that negative 1, which will give us a negative 6. On the second term, we'll have x to the negative 3 plus 1 will be negative 2, and we'll divide the coefficient by that negative 2. This negative 1 divided by negative 2 will be a plus 1/2, and plus c. And on our last example, we haven't talked about how to work with this indefinite integral with a quotient, so we're going to get out of having a quotient. I'm going to go ahead and divide all these by x because they all have x's there. I can simplify this down to 2x squared minus 4x plus 7 dx. The x squared, we'll add 1 to that to make it an x cubed, and divide by that new exponent. Divide by that n plus 1. Minus, this x to the first will become an x squared, and dividing by 2 will give us a 2 out in front. The constants, those are the easy ones. This 7, its antiderivative is 7x. And then our plus c. So what's the purpose of this new skill? How does this connect with where we started back at the beginning of this lesson? What we've built up to is what's known as the first fundamental theorem of calculus. And it states that if we have a continuous function on a closed interval, and we can find the antiderivative big F of our function little f, then the integral from a to b of little f of x dx equals big F of b minus big F of a, or the antiderivative at b minus the antiderivative at a. And so the connection I want you to make is, back at the beginning, we were working with the integral from 1 to 4 of t squared minus 6t plus 2, some velocity function on an interval 1 to 4. It's a polynomial, definitely a continuous function. The antiderivative of v of t would be our position function, would be this x of t. And the connection I want you to make is, we talked about this back at the very beginning. This integral represents a change in position, and I could also get the change in position if I just did my position function at 4 minus my position function at 1, which is exactly what the first fundamental theorem of calculus states. The definite integral of any function on a closed interval will be the antiderivative at the end value minus the antiderivative at the beginning value. Final position minus initial position, in this case when dealing with velocity. And so looking at our final example, let's use what we have to find the definite integral from 6 to 2 of 3x squared plus x minus 2. What this states is that we are going to go ahead and find our antiderivative first. So let's go ahead and do that. The antiderivative of 3x squared will be x cubed, and dividing by 3, that'll give us a nice 1 out in front, plus this x to the first will become an x squared, and dividing by 2 will give us a 1/2, minus 2x, plus c. And one thing we're going to add to help us out, this little bar is just going to signify that we're still working from 2 to 6. And this first fundamental theorem states the area under this curve will equal this function evaluated at 6 minus this antiderivative function evaluated at 2. And so this first group will represent our antiderivative at 6, or if you want to put it in context, you can think about that as a position at 6 given a velocity, and it will be 222 minus our antiderivative at 2, which will be 6, and give us an overall area bounded by this curve between 2 and 6 at 216. And the nice part is you do these problems and you start working into your practice, very easy to confirm. Go to our calculator, Math 9, we'll do the integral from 2 to 6 of 3x squared plus x minus 2 with respect to x, and confirm our 216. And so that does it for 6.4, a very important lesson for us. Again, that name is not meant to be misleading. This first fundamental theorem is going to be fundamental to everything we do from here on out. And this skill of finding the indefinite integral is necessary in order for us to apply this theorem to problem situations. So please make sure, review and summarize these notes, and get into your practice working with indefinite integration and applying the first fundamental theorem of calculus. And thank you for watching.